Hey everybody. Let's get ready to start. Thank you. All right. Hi everybody. Thanks for coming to our to this OWASP meetup. Well, to offset the previous presentation, I'm going to do something quite technical. So I hope it evens out in the end. Usually it's a 1 hour presentation, but I condensed it a bit to 30 minutes. So we'll still go over technical details, but it's not going to be insanely technical, but hopefully we'll get the point across. So we're going to talk today about automated zero-day discovery, and specifically in binaries. In JFrog, we love binaries. So we really want to find vulnerabilities in those and see how to do it with open source tools. That's the cool part. So some high level algorithms, but then also diving into some technical details on how to do that. So I'll introduce myself. My name is Shachar Menashe. Work here at JFrog, basically in charge of security research. So both myself and my guys doing CV analysis, guys and girls doing CV analysis, malware analysis, zero-day research, these kind of things, fun stuff. Me, myself, I've been working, even beginning with my first job, just hacking stuff like security architect, security engineer, reverse engineer, you know, the fun stuff. So today I want to talk about really two things. First of all, we're going to be focusing on Ghidra, which is the disassembler. It's okay if some of you might not know it. I'm going to explain a bit, but I want to show two things. First of all, how today with open source tools that really are outside, you can start messing around with automatically finding vulnerabilities, even in binaries. So I'm not talking about, okay, you got a source code and you're going to run it through some linter or a source code analysis tool, something like that. Really everything with open source and see what we can do. So I'm going to talk about the high level algorithm and introduce some concepts that are available with disassemblers like Ghidra. And then I'm going to talk about a specific CVE that we were able to identify in the past using these automated methods. So first of all, what is Ghidra and like why are we even using it and why do we actually recommend it for these sorts of endeavors? So first of all, if you're searching for vulnerabilities in binaries and you don't have the source code, you're going to have to use either a static analysis tool or a dynamic analysis tool or both of them. Ghidra is mostly a static analysis tool. It's a disassembler. So is anybody here by show of hands maybe used Ghidra before? Just wondering. Okay, and anybody by show of hands used IDA before? IDA disassembler? Yeah, no, that's the third point yeah, Ghidra is cheaper. So yeah, both IDA and Ghidra, these are tools that basically you take a binary, a compiled binary, so a exe, an ELF, Maho, if you're unfortunate enough to work on OS X, and you dump this, you throw this binary in the tool, and what it gives you a listing of the opcodes or assembly commands that are in the binary. So basically it's the source code, but in a very unreadable way. So reverse engineers, what they do is they take this listing of assembly and try to figure out what the original code is. It's tough, but it's possible. And today, even both IDA and Ghidra and other disassemblers have even more advanced capabilities that are decompilation. Basically taking a binary and let's say that the original binary was written in C, you can take the compiled binary and get the C source code out of it. The source code looks really bad. It's not very readable, but it's more readable than assembly. So part of the reasons why we're using Ghidra, it supports this compilation for every type of binary you throw at it. So we can throw, like I said, like a Linux binary, Windows binary, Mac binary. It can be any architecture like ARM, MIPS, x86, of course, things like that. And it will happily take it and decompile it, and all of it for free, unlike IDA, which it's like $2,000 for the disassembler and another $1,000 or something like that for each decompiler. That's a really cool tool to use to do that. And another very important thing is that Ghidra actually gives you a very great API to look at things automatically, like not just looking at it manually, like, okay, here's the source code, but even doing analysis on that decompiled source code. And this is what we're going to look at. So before diving into the details, what do we even want to do? We want to find zero-day vulnerabilities, and we only have the binary. What we're going to do is mimic a manual researcher, actually. And specifically, what we're going to do is figure out in the binary. Okay, that doesn't work that well, but I hope you can see. Step number one will be to figure out in the binary where user input sources are getting into. To exploit a vulnerability, there has to be some input from a user, like let's say a request to a web page or something you're reading from a network socket. There has to be some input source because this will be the channel where the attacker will send the malicious exploit, basically. So first of all, there has to be a user input source, so some external input. Second of all, there has to be some dangerous function. And third, there has to be a data flow path between the source and the sink, the dangerous function, without any interruptions. So we're going to see some examples of that, but just with this example, does anybody, maybe anyone can say from this graph what kind of vulnerability this looks like? Yeah. Code execution, but through what vulnerability? The impact would be code execution. So usually code execution is a good partial answer. Usually when you have unfiltered input that get to the system function, it's usually a command injection vulnerability. Like usually some of the input will get from the attackers to like a shell running function, and then it will cause a command injection vulnerability. It's very rare that the attacker can actually control all of the input to this function, but very often the attacker can control some of it. So this is what we're trying to look for. We're trying to automatically map all the places in the binary that input can get from, and then seeing all the dangerous type of functions that if input gets there, there's a 0-day, basically. So the way we're going to do that, I'll just talk about it a bit in high level. First of all, we're going to take the binary and we're going to translate the assembly into what Ghidra calls, or a lot of tools call, intermediate representation. It's going to be something that is not exactly source code, but it's a bit better than assembly, and we can actually work with that. We can analyze that. Then we're going to do data flow analysis. We're going to understand, okay, there's some input being read from a socket somewhere. This data is going to flow through several functions, and we're going to see where it reaches eventually. And in parallel, we're going to do something very important. We're going to understand what are some helper functions in this binary. The problem when we're working on embedded, everything is statically linked. So actually a lot of functions in the binary, you don't know what these functions are. When you compile something, all the function names gets lost, assuming you don't have debug symbols, because usually like 99% of the cases you don't have that. So you actually have to understand some very basic functions like strcpy, malloc, like string copy functions, allocation functions. Like I showed in the example before, even system, like it's a function that you need to understand. And these are the dangerous functions, and we need to somehow understand that what functions these are. So we're going to find that out through emulation. That would be the second part. And then when we put all of these parts together, we can say statements like, oh, okay, there's an argument to system, which is a dangerous function, and it's calculated from the output of receive, which receive is a function that receives data from the network. And again, if we find a source, for example, from the network, there's data flow all the way to dangerous functions, and there's no filtering in between, then that's a vulnerability. All right. So now diving a bit into the technical part. So basically, it's very hard and it's very non-robust to do the analysis I'm talking about, like data flow analysis on straight assembly. So here we can look at disassembly of ARM, like thumb instructions. This is the original source code, sorry. So it's like a call C source code, call to memset, just writing two null values to some variables, and then just calling a function with a pointer. So these 4 lines translate to quite a lot of lines in assembly. And the problem is you don't really understand what are function arguments here. You don't understand where the variables are. You don't understand how they flow. This is what's tough about being a reverse engineer. You need to understand all these things. But today we have decompilers, not just disassemblers. So for example, Ghidra can take this mess and show you something that is, let's say, similar to this. It won't show the variable names, etc., but it will show something similar. And this is how the internal representation of it looks. And this is what we're going to run our analysis on, actually. So first of all, you can see the Ghidra's internal representation language is called P-Code. So first of all, it has its own opcodes, but it has high-level opcodes. It's sort of a pseudocode. So for example, if in the source code, if in the disassembly, you can't see what the arguments to some function is. So Ghidra actually figures it out. So we see these call arguments. They tell you already exactly, what's the function that's being called, memset. And you can see, for example, that the first input is the output of this P-code, which is just a pointer dereference. And the second input is a constant with 0. Here in the disassembly, it's a bit harder to see. And in some cases, it's really hard to see. Like it can come like, it could be mangled. It could come in between other unrelated register moves. So here we have like an intermediate representation that we get something that is a bit more closer to the source code. And the most important thing is this is cross architecture, cross executable, whatever. Like it doesn't matter if I compile this C code to, again, Windows, Linux, Mac. It doesn't matter if I compile it to ARM, etc. All of these things that I said will vastly change the assembly, like calling conventions, all sort of things, but it will not touch the P-code. I will get the same P-code. And then that's great. I can write my scanner one time and it will work on any format. So that's also a very important advantage of like using the intermediate representation and not the assembly. So now this is kind of the hardest part. And I'm going to talk about some solutions here. It's not exhaustive, obviously, talking about some solutions that did work for us, for example, in real life. But this is quite a hard problem. So even in source code, it's very hard to understand where external input is coming from. External input, I mean like input from the network or even reading from a file, reading from an environment variable, anything that an attacker can actually influence in order to get his payload into the dangerous function. For example, if we have a dangerous function like system, like I said before, but it gets constant input, it's not interesting. It's not a vulnerability. I, as an attacker, or not an attacker, but as a defender, of course, I, as a defender, can't influence the input to that function, and it's not interesting. It's not a vulnerability. So let's understand. Let's see a few cases where we can understand that actually external input is coming to a function. So we have high accuracy sources. For example, syscalls, which for syscalls, you can understand from the binary which syscall it is, usually. Like you see a piece of code and you understand, okay, this is calling syscall number X. Usually you can understand that in ways that I won't delve into right now, but you can. And for example, there are some syscalls like receive, getenv, fread. Some of these are local calls. I'm a bit mixing and matching, but just to make it a bit simpler. So for example, if you see a receive call, okay, this is getting input from network. if you see a getenv input from environment, if you're seeing fread, then input from a file. And that way you can understand, okay, this is a good source point that I can say everything that comes from this input is tainted, like it could be attacker controlled. Another interesting thing in Ghidra that we worked with, which was very cool, if you're working on a specific embedded device and you know like what CPU you're working on, and it's mostly for ARM-based CPUs, Ghidra has a plugin called SVD Loader, and it will tell you, oh yeah, if you're reading from register at address 1000, it's actually input. It's like UART or USB or even Ethernet. So that's something really cool that you can work with. Again, everything is open source. If you know the exact board that you're using, it will map everything out for you. So this is kind of high accuracy sources that you can use to determine from the binary where the input is coming from. There's also score-based sources, which worked really well for us, which was pretty funny because it's things you might not consider. So for example, let's say you can identify the functions N2HS and N2HL. These are functions that are used when writing network code that converts integers from like big endian to little endian, like from network notation to host notation. The function by itself doesn't do anything interesting, but like part of the concept is understanding, hey, if I have this conversion, it means this integer is coming from network. So maybe actually this integer is controllable, and we found a lot of interesting integer overflows, for example, with this. So, so you can be creative in the binary and say, okay, if this manipulation is caused on the data, maybe it's coming from, external inputs. Also, something that really works for us well and maybe easier in this case is just protocol excerpts. You see some function and it has a lot of strings related to HTTP or FTP in this case. You can say, okay, I'm saying that all of the output of this function is tainted. Like all of the output of this function, I assume it's coming from either like HTTP or FTP sources, which I consider external sources. And of course, if you have more of these strings, you give it a higher confidence score, and that's how you build a list of sources. So now you have your list of sources, but you know where to start from, but you need to know where to end. So this is actually easier usually. You just take out each type of vulnerability and you define what kind of functions are the dangerous functions for this vulnerability. And then usually finding these functions is not so tough. So for example, for command injection, like I said before, if arbitrary input is going into system or popen, it's bad. This is the dangerous function in this case. For buffer overflow, it's functions like memcopy or strcpy. If it gets unbounded input, then again, it's a big problem. So these are more basic things. There are more advanced things that you need to not look for a function, but actually look for a series of opcodes or a series of statements. So for example, instead of memcpy, it doesn't have to be like a string copy that's caused, buffer copy that's caused by a function. It could be just a loop in the program. So then, again, with the static analysis, you would need to go over the code, find all these loops, and label them as equivalent to memcpy. By the way, this is something that the decompilers do for you. Like both IDA and Ghidra, if they see a loop in the code, they can say, oh, this is just like inline memcpy or something like that. So basically for each type of CWE or each type of vulnerability, we say, okay, these are the functions that are the dangerous functions for these CWEs. The last part is the parallel part, which is pretty cool. So usually with embedded binaries, for example, you might not even know which functions are library functions and which functions are just local functions. For example, in the example before, we said, oh, just look for strcpy. But if it's an embedded binary, it might not even be written. You might not know that this is strcpy. So how are you going to find all these utility functions? So something really cool, and again, it's an open source tool called Sybil. Basically, you can, it's an emulation engine called a divination engine. It's an emulation engine that basically comes with some predefined rules, and it says, okay, if I'm running a function and I give it this input and I get this output, then like in a lot of the series of rules, then this is memcpy or strcpy or strchr, any C library function. So basically you're running the function, and there's no like you can take a piece of the binary and just run this piece without compiling or doing anything. This is something that also researchers do manually a lot of time, just to understand what the function does. They just run the function. Sometimes it's easier. And this tool comes with a predefined set of rules that says, okay, if for this type of input, I'm getting this type of output, then I understand that this is the function. So with this tool, you can just run it on arbitrary functions in the binary and understand all these utility functions, which we need to understand in order to map out our sinks. So now it's kind of the last part, the data flow analysis. So what do we do with that? This is quite a tough problem. Even with static source code analysis, it's not that easy of a problem. Like to understand the flow of the data, like, okay, I have a variable here. Does it reach any other functions? If it's a global variable, like who uses this variable, who writes to it, who reads from it? So this is not an easy problem, and in binary, it's even a harder problem. The cool thing in Ghidra, it does give you an API to get started, which is something that you can use. It's called get forward slice or get forward slice to P-Code ops. Basically, both in the UI and API, you can highlight a variable and say, okay, now find everybody that uses this variable. And it will, like I showed here, it will like highlight, okay, phvar2, it's dereferenced here. And then the output is being put in this variable. And then it says, okay, so this variable is also tainted from the initial one. And then it will keep looking at all the places that use this variable and so on and so forth. There's two catches. So this API you get for free, but there's two catches. First, it doesn't handle stack variables that well. So you need to take that into consideration. And second, this is an intra-function API. So it will work for inside the function, but it won't show you anything that's outside the function, which is, of course, very problematic because then it really limits like the kind of vulnerabilities you can find. So here you need to take a bit of initiative and write some additional code yourself. Basically, the idea is that we're going to apply this function, the get forward slice, just recursively. We're going to apply it on a function, see what goes out of that function, and then apply it on the next function with the input that we got from last time, and so on and so forth, and then gather all the results together. So this is something that Ghidra doesn't provide, but it's very doable, for example, in Python, just to write that yourself. Okay, so we talked about the data flow analysis and finding out the functions, the sources, and the sinks. But eventually, it's not enough that you have user input that flows in some way to some dangerous function. Why? Because of filtering, of course. So for example, let's see some example. For example, if we're looking at a buffer overflow vulnerability, then there could be, even though like the user input flows to strcpy, it doesn't matter because here we check that if the length is too big, we just kill it. We don't allow it to flow. Same thing for command injection. Here we check for some characters, and if the user input contains these characters, we don't call the dangerous function. So we have to also another thing that we saw a lot actually. A lot of the times there will be just a straight up string comparison and comparing the user input to some fixed input. And if it's not this fixed input, then boom, get out of the function. So of course you need to take all of this into consideration. Otherwise you'll get a lot of false positives. Oh, sorry. So again, in the longer presentation, basically you can check for these examples one by one, just with basic static analysis because you have the decompiled code. There are more advanced ways to do that. For example, symbolic execution and emulation. I just won't get into them right now because it will take too much. But we'll send also an extended version of the talk where we get into that as well. But the idea is to identify each type of these checks and then just check for them yourself manually and say, okay, if there's this check, then I'm not continuing the data flow analysis. Okay, so now let's talk about a real case where we applied this and found a vulnerability. So for example, CVE 2021-31228. It's part of a collaboration actually that we did in the past with Forescout, which was really cool. And found a set of vulnerabilities on embedded TCP/IP stack called niche stack, which is pretty funny. It wasn't that niche. It actually affected a lot of devices. So one of the vulnerabilities here was a denial of service. So here there was a signed comparison that just leads to a huge overflow. So the problem here is that, let's say that we control len. So here len is signed int and not an unsigned like it should be. Here there's a comparison being done. But of course, if len is negative, then it will pass this comparison, which it shouldn't. And then in the memcpy, because len is negative, it will come out to a huge value and crash the server. So so let's see an example of how we can find something like that. So here, like eventually this was the source function. Here we have some unknown function and then an assignment to a struct. So after running the divination that I talked about, Sybil, in this case, so it actually figured out that this function is A2L. So it converts a string to an integer. So this is something that we also consider as potential user input. Just to understand, like, okay, we don't even see all the code, but this is the function. So you would probably think, and this is like even decompiled, as you can see, like in the source code. This is horrible, of course. Like you'll never understand from static analysis, like very fast static analysis. You probably won't understand. Okay, this is A2L. Like it will take, even for experienced reverser, it will take a few minutes, and for not experienced, maybe never. But this is the beauty of running it in emulation. You can just put some strings, get some numbers, and understand, okay, this is actually A2L. So this is what happened in this case. So because this is A2L, we said, okay, this is one of the interesting functions that we look for. Basically, we tainted lvar7. Then a line after that, lvar7 is tainting a struct and a specific field in a struct. So we're saying, okay, if anybody touches this field, again, it's going to be tainted. This is the data flow analysis algorithm. Again, adjusting for time, this went on for a few functions. It's also important to note that one of these flows was a data reference, like it wasn't trying to move something, it just referenced the struct. So we have to take that into consideration as well. And eventually, it reached this function, get bound search. And like I said, it reached the len argument. So here, just to clarify, so for example, if there wasn't an if check here, we could just say, okay, this is a heap overflow, because you can just copy how many ever bytes you want because you control length and you get an overflow. Because it's a signed integer, then we classify it as a signed comparison bug, which sometimes is exploitable, sometimes not. In this case, it was exploitable. And of course, if it was unsigned, then we would just say, okay, this is not a vulnerability. So these are all the possible cases that could have happened here. Thanks. Okay, no, right on time. Good. I was wondering if to do Q&A, but